today we are going to talk about the optical properties of materials. So far we have covered all the mechanical properties of materials. However, there are many cases where the optical property becomes important along with the mechanical property. Let us say we are designing an oven for a very high temperature and we want to carry out some experiments. That means what is happening inside the oven. For example, a polymer is changing its glass transition temperature and you want to visualize that how it is happening. Now in all such cases you actually need to send light from outside which should go penetrate this particular oven casing, and it has to go inside and get reflected back, from which you get the information. So in this case that part of the oven which is has to be transparent with respect to light has to also be oven like, that means high temperature proof. So it is a special mechanical material where both temperature and optical property will be important. Again, there are other materials, other cases where it is optical property which is to be matched with magnetic property, or optical property which is to be matched with some of the dynamic properties, etc. So thus optical property becomes important in many of the applications. So what we are going to first while initiating the discussion today, and later on we will take it further, we are going to first talk about the basic concepts related to the optical property. So we are going to talk about the basic concepts, then the optical properties of metals first let us discuss, then the optical properties of non-metals, and then some applications of the optical phenomena. So these are the four things that we are going to tackle. Now the first important thing is that when we are talking about the optical property, we are talking about the electromagnetic spectrum. In that electromagnetic spectrum of the wavelength, we have shorter wavelengths at one extreme, which is like the gamma rays, and longer wavelengths in the other extreme, which are like the radio waves. So as the wavelength increases, the lambda, we are starting from the gamma rays which goes somewhere up to 10 raised to the power minus 4 nanometer or so. 1 nanometer is 10 to the power minus 9 meter. So you can imagine that how small that wavelength is. Then there is X-rays there, and then from X-ray when the wavelength further increases, then we come somewhere in between. You have the ultraviolet radiations, and then we have the entire visible part of the visible light. In that visible light, where exactly our eyes are also very sensitive, it starts from 400 nanometer of wavelength and it ends at 700 nanometer of wavelength. So at the very high low wavelength and high energy end, we start with violet, then there is indigo, then there is blue, green, yellow, orange, red. Red is around 700. So that is what is the spectrum of the optical part, which we generally call as the visible light. Then once that wavelength further increases, we come to the infrared radiation types, and that goes somewhere up to millimeter level. If the wavelength is even more, then we come to microwave, and if it increases further from the meter level to kilometer level, then we come to the radio waves. Interesting thing is that this picture we have discussed from shorter wavelengths to longer wavelengths, but in terms of energy it is just the reverse. What it means is that those which are having the shorter wavelengths, like the gamma rays, you can see that they have the highest energy in terms of electron volts, and then gradually as you the wavelength increases, the energy actually reduces and the radio wave would have the lowest amount of energy. For example, if you consider it in the visible spectrum itself, red has an energy of about 1.62 electron volt, orange 2.08 electron volt, yellow 2.15 electron volt, green 2.52 electron volt, blue 2.73 electron volt. It is increasing gradually, and violet is 3.17 electron volt. Another interesting thing you might have noted that this energy is really not, it is distinct, there is no doubt in it, but it is not very evenly spaced. That is very interesting thing that you can see here. However, the colors are very distinct. Now, we are talking about the electromagnetic radiation. Now, in the electromagnetic radiation, from the functional point of view, it is actually a combination of two time varying waves. One is the electric field wave and another is the time varying magnetic field. So, if you denote one in this manner, as it is here, okay, as the time varying electric field, suppose, then the other one is the time varying magnetic field. So, it is just transverse to the two. So, these two waves, that is why we say that for an electromagnetic wave, these two fields, the electric field and magnetic field, they are just always coexistent with each other, and the speed of the electromagnetic radiation at vacuum for both of them is close to 3 into 10 to the power 8 meter per second. The velocity at any particular medium, in fact, is inversely proportional to the square root of epsilon 0 and mu 0, where epsilon 0 is the electric field permittivity of vacuum and mu 0 is the magnetic permittivity of vacuum. So, this is interesting. What it means is that if suppose you consider a particular medium in which you have high electric permittivity, but low magnetic permittivity, but it is the product that would matter, and that would be the velocity of the electromagnetic wave in that particular medium. In vacuum, epsilon 0 is 8.854 into 10 to the power minus 12 farad per meter, and magnetic permittivity is 1.257 into 10 to the power minus 6 Henry per meter. So, in one case the unit is farad per meter for the electric field, and for the magnetic field it is Henry per meter. We have to keep these points in our mind. And how do we calculate the energy? Well, that is E equals to h nu, where h is the Planck's constant, right, which is known to you, and nu is the frequency. That means, as I already told you, that as you know, for example, the frequency of each of these cases of this light wavelength is known to you, violet, blue, green, or these things. You know the wavelength, you also can then find out the frequency, and as you know the frequency, you can actually find out what is the energy content corresponding to this. In fact, the wavelength and the frequency, as you can see, is simply related by this relationship that nu equals to c over lambda. In other words, if I know lambda and I know the velocity in the medium, then I know what is going to be the frequency. So, I should be able to find out that what is the energy for a particular wavelength. Okay. Wavelength we usually measure in meter and velocity in meter per second. So, these are the very basic fundamental things that we have to keep in our mind corresponding to the electromagnetic waves. Next is that light as an electromagnetic wave, when it falls on a solid, what happens to it? Well, the incident light, when it falls on a solid, it can either be reflected or it can be absorbed, scattered, and or transmitted. So, we can write that I0 incident light is going to have at least three parts: IT, IA and IR. That means this is my incident light I0. Some part of the light may get reflected, that is IR. Some part of the light may get absorbed inside. It may not absorb for a very long time. We will see that sometimes it absorbs and then it emits. And some part of it may get actually transmits. So that is what is our IT part. Absorbed is IA and reflected is IR, whereas the incident is I0. Now, we always say that there are these three types of materials. One is the transparent material. So when we are talking about transparency, it means that most of the light is actually transmitted through the system like a single crystal. Sometimes we say that it is translucent. Well, translucent means some part of the light is actually absorbed and some part of the light is getting transmitted, that is like the polycrystalline dense. And sometimes we say that it is opaque, and when we say that it is opaque, what it means is that this does not occur. Okay, so the light is absorbed and may be partly reflected back, like polycrystalline porous materials. So thus different materials can have this type of different optical property based on whether it allows the light to pass through it, it absorbs the light, or it reflects the light. Let us first discuss on the metals, that is the optical properties of the metals. Now, all frequencies of visible light are absorbed by metals because it has continuously available empty electron states which permit the electron transitions. I already told you that metal has always as if a cloud of electron. It has never like a lack of any electron. So if you take a metallic piece and shine light on it, so the photon are going to get absorbed by the electrons at the low energy state, of which it has an infinite supply, let us say. So and then as they get they are absorbing the energy, some of them jumps towards the higher energy states. So there is a Fermi energy level, and there are some field states and there are some empty states in the metal. So as the photons get absorbed, they go from field state, they jump towards the empty states which are of higher energy states. So the incident radiation having frequencies within the visible range excites the electrons into unoccupied energy states like these states, okay, above the Fermi energy level. So the incident radiation is absorbed, and hence metals are opaque because it is not allowing any light to pass through it, because it uses the entire light to excite its own source of electrons, and that is why it is opaque. Now the Fermi energy is the maximum energy occupied by an electron at 0 degree Kelvin. That is the way it is actually defined. The change in the energy of the electron, delta E, is equal to the energy of the photon, because this is the energy that it is absorbing. So the change in delta E is actually the amount of energy that is coming through the photon. What happens? It does not stay in that position. After it gets the energy, then it re-emits. Re-emission of a photon of light takes place by the direct transition of an electron from a high to a low energy states. So it first gets excited, go to the high energy state, and then it re-emits the photon. Okay, it does not hold that energy with it. Metals are opaque to low frequency radiation, for example radio waves to about some middle of UV rays, but they are transparent to high frequency radiation. So high frequency radiations that these source of photon they do not absorb that. So those waves can actually, high frequency waves can actually get passed through it. But if it is of a lower frequency, then this situation always happens that it absorbs it, the photon goes to the high energy state, and then the photon emits this energy at a time scale. In fact, later on we will tell you what happens when it emits this energy back. So, here the same thing we are telling, that an incident photon energy, let us say h nu, h is the Planck's constant, okay, and nu is the frequency of the incident light. And from the field state at the Fermi energy level, the delta E energy is giving the h nu is coming as the source of the delta E, and it is jumping from here to the high energy state. Unfilled electron states are adjacent to the field states, so it just does that, and near surface electrons absorb the visible light in the case of the metals. Now, most of this absorbed radiation is actually re-emitted from the surface in the form of visible light of the same wavelength which appears as the reflected light. So, when we see that some light is reflected, it is not the same light which actually is incident on the system. That is what we have to understand, that light falls on the metallic surface and then that light gets absorbed by the electron. The energy that is absorbed by this electron, that it absorbs and it goes to the high energy states, I told you, but it cannot be sustained at a high energy state. Why? Because minimization of energy or maximization of entropy is there in the nature of every system. So, as soon as it goes to the excited state, it again tries to jump back to the low energy state in order to minimize the energy, and as a result this photon is going to emit the energy which is approximately of the same frequency as the incident energy that is coming, and then it is coming back as a reflected energy. Now, it is this reflected energy that I am actually watching, but this reflected energy is coming from the electrons of the metal. That is the important thing. The source is inside the material, we have to keep it in our mind. The reflectivity of metal can be actually measured in terms of the ratio of this incident ray and the the incident energy, and the IR is the reflected energy. So, the IR over IO ratio, which is generally between 0.9 to 0.95. A little bit of energy gets absorbed into the system, but generally it is of very high reflectivity, 90 to 95%. In fact, before glass was discovered by people, actually shining mirror was used to be used as mirrors. Okay? So, you can easily imagine that people used to use for example shining copper surfaces etc. as their mirrors. Of course, there is a problem there that copper, for example, will get oxidized pretty fast. So, that is how the glass is much better, because it does not get oxidized so fast, but it is because of this high reflectivity you can easily imagine that you can see your image very nicely on the metallic surface, because the light wave which will get reflected from your body and then go to the this metallic surface will actually almost 90% to 95% will come out, and hence you will be able to see this and you will be able to see the image. Now, we will talk about the non-metals. So, with regard to non-metals, 4 optical phenomena are important: reflection, absorption, refraction and transmission. So, let us look into them one by one. First of all, we will talk about the refraction of a system. So, when light photons are transmitted through a material, they actually cause polarization of the electrons, and in turn the speed of the light is reduced and the beam of light changes its direction. Okay. So, from the vacuum, for example, the light is coming to any such non-metallic system. Suppose it is coming into glass. Okay. So, the moment it is coming inside the system, there is a polarization and the speed of light will get changed, and as a result that speed of light as it gets changed, it will not be able to progress in the same direction, but it is going to get changed. Now, refractive index n is nothing but the ratio of speed of light in a vacuum to the speed of light in a medium. So, any medium is going to slow down if the light comes from vacuum and to a medium. Let us say sunlight is coming from space to the atmosphere of Earth, it is going to get a refraction because it is going to get slowed down in the medium. Now, for any medium, what will be the speed of light? Well, for any electromagnetic system, I already told you that it is actually 1 over square root of epsilon mu, where epsilon is the permittivity and mu is the permeability of the medium. So, if I want to calculate n as C over V, then it is simply square root of E mu over square root of E 0 mu 0. In other words, it is square root of epsilon r mu r, where epsilon r is nothing but epsilon over epsilon 0 and mu r is nothing but mu over mu 0. That means relative permittivity and relative permeability will come into the picture. Now, also we know that the Snell's law you must have studied earlier, and that says that if my incident angle is theta I and reflected angle is theta r, or refracted angle is theta r, then n1 sin theta I equals to n2 sin theta r. Okay, this is an important relationship which we will later on we will see that for optical fiber we are going to use this principle. Now, the refractive index of some of the very common materials, let us say silica glass, ceramics, is a refractive index of 1.458. So, quite a low refractive index. Then we have borosilicate glass 47, 1.47, 1.51, like that. Al2O3 is 1.76. So, that is the kind of refractive index that you are finding in the ceramics. In the polymers, it is even lower, like 1.35 for polytetrafluoroethylene, PTFE we call it. Then polymethyl methacrylate 1.49, polypropylene 1.49. In fact, some of them are somewhat similar to the glasses. That is why some of the polymers today are used as glasses. Polyethylene 1.51, polystyrene 1.60. So, it is possible today to have transparent, optically transparent systems both from polymers as well as from ceramics. That is good because ceramics are brittle but polymers are not. Now, let us come to the reflection. Reflectivity is defined as the fraction of light that is reflected at an interface. So, it is a ratio of IR over I0. This we have also discussed when we have discussed about the metals. So, if the light is normal or perpendicular to the interface, then the R can be actually derived to be something like n2 minus n1 square and n2 plus n1. So, n2 minus n1 by n2 plus n1 whole square, where n1 and n2 are the refractive indices of the two media. Higher is the refractive index of the solid, the greater is the reflectivity of the medium. So, in comparison to between the two materials, if the the refractive index is higher, then we can say that R is actually going to be more for this particular material. Now, in metals, the reflectivity is typically, I told you, of the order of 0.90 to 0.95, whereas it is just the reverse for the glass. It is about 0.05, 0.05. Okay. So, what it means is that the value of the refractive index is very, very high in the metals, and as a result you get a very high refractivity in the metals, whereas for glasses it is just the reverse. High reflectivity of the metals is also one of the reasons that they are opaque. Anyway, we have explained the fundamental reasons to you. Now, let us come to the absorption part of it. When a light beam is impinged on a material surface, portion of the incident beam that is not reflected by the material is either absorbed or transmitted through the material. The amount of light which is absorbed by a material actually can be calculated using Beer's law. So, here IT is the transmitted light intensity and I0 is the incident light intensity. Suppose if you know the absorption coefficient beta and a sample thickness L, then you can say that the transmitted light intensity is I0 e to the power minus beta L. Okay. So, the intensity of IT will actually, with respect to the thickness as well as with respect to the absorption coefficient, it will follow an exponential way of actually falling down. Okay. So, with respect to length or with respect to, if I consider the absorption coefficient beta, either of them, it exponentially falls down. So, that is about the light which is absorbed in the system, that is the IT part of it. Okay. Now, materials that have large beta values, they are considered to be highly absorptive because they are taking most of the transmitted most of the light inside energy into the system. There are several absorption mechanisms. One is known as the Rayleigh scattering, where the photon interacts with the electrons and it is deflected without any change in its energy. So, that is called the Rayleigh scattering. This without any change in its energy is very, very important. Okay. So, photon simply interacts with the electron and gets deflected. For example, the sunlight gets deflected and the blue color you see all over in the sky. So, it is like a Rayleigh scattering. There is also Tyndall effect, where scattering occurs from particles which are much larger than the wavelength of light. So, any colloidal suspension for that matter shows this Tyndall effect. Compton scattering, where the interacting photon knocks out an electron, losing some of its energy during the process. So, not like Rayleigh scattering. In the Compton scattering, the photon during the impact loses some of its energy and then the scattering takes place. And then the photoelectric effect, when photon energy is consumed to release an electron from atomic nucleus. This is the famous effect for which Einstein got his Nobel Prize. So, there are such various mechanisms of absorption of light: Rayleigh scattering, Tyndall effect, Compton scattering and photoelectric effect. Now, about the transmission of light, IT is very similar to the reflection. Here there is a law which is very similar to Beer's law. It is IT is now I0 into 1 minus R whole square times e to the power minus beta L. So, that is what is the IT. So, if I0 is the intensity of the incident beam, then part of it gets reflected IR, which is I0 times R, and part of it gets transmitted, which is I0 times 1 minus R whole square times e to the power minus beta L. So, this is what is when the light is transmitted from the system. Now, I told you that material absorbs energy, but I told you that when it absorbs the energy, then electrons go to a higher energy state, but it cannot sustain the higher energy state, because it has to come down to for the minimization of energy. So, it will actually emit the energy back and it will come down to low energy state. If this emission of radiation occurs, and this entire phenomena is what we will be calling as luminescence, but if this occurs within 10 raised to the power minus 8 second after excitation, then the luminescence is called fluorescence, and if it takes longer than 10 to the power minus 8 second, then it is called phosphorescence. Ordinarily, pure materials do not display this phenomena, but some special materials called phosphors have this capacity. For example, yttria, ZNS, cadmium sulfide, and a very complex one which contains barium, magnesium, aluminum, oxygen, etc. There are examples of many applications of these effects like fluorescent lamps, CRTs, plasma video display, white LEDs. In all of them, in some way or the other, exploits this, the fluorescence and phosphorescence of a phenomena of an optical property of a material. The second interesting case is called photoconductivity, which is actually important for materials like semiconductors. If you bombard the semiconductors by photons, then what happens is that the energy in this case, which is equal to the energy in the that can create the electron hole pairs, that means is greater than the band gap, they actually can be used to generate a current, and that is known as photoconductivity. So, it is different from the photoelectric effect, because in the photoelectric effect the photon is actually absorbed by the electron itself, whereas here it is the electron hole pair which gets this energy, the band gap energy, and then that actually excites the flow of these electron hole pairs, and that generates the current. So, this current which is produced through photoconductivity is directly related to the incident light intensity. As a result, these light meters you see in cricket matches, etc., people use, they are actually based on this photoconductivity of the incident light. Okay. So, it is based on the electron hole pair. Okay. For example, cadmium sulfide is one of the very common example in light meters. And today's solar cells, they are also based on mostly the photoconductivity. So, this is another very good application of the optical property. The third and the most important one, and towards the end of this course we will show you some of these applications to lasers, is actually light amplification by stimulated emission of radiation. So, in this case, for example, if we see this particular case that you have a ruby crystal and then you have a flash lamp from which you are providing energy to the system, you see in the case of luminescence the energy is coming out, but it is incoherent because it may have different, the phase relations continuously changes, whereas laser emission is very much coherent, constant phase difference, and the same frequency will be emitted. So, when you consider this ruby, which is a single crystal of Al2O3 doped with a very little amount of chromium oxide, or yttrium aluminum garnets, YAG we call them, or neodymium helium neodymium lasers, this type of materials, when you excite them, what happens is that you first get these atoms in the excited state, the incident photon is coming, and then some of the electrons are getting excited to the high energy state. But after that what happens is that they actually start to excite more of these electrons in the system, and then this happens, this gets multiplied, and then that actually becomes a source of the coherent light emission in the system. So, this kind of a system at the end generates a coherent beam, and that coherent beam can be used for many detection of physical properties of materials. So, we have seen here the various properties of we have discussed today, the various optical properties of metals and non-metals and some of the very important optical phenomena. In the next lecture, we will study the optical fibers and its principles and types and various applications of optical fiber. Thank you.